So I'm going to go quickly through the first 5 or 6 problems from the assigned homework for the Newton's Laws of Motion chapter. And what I would recommend is you read the question head and then pause the video, read the question head, and then come to see the answer, because I'm not going to be dwelling on parsing the information from the question head. Okay, let's get right into it. Question number 6 is that question that was saying there's a projectile that it has a mass of 5 kilograms that the engineers are going to launch somehow into space, and they find that if they act with a net force of 4.9 times 10 to the 5 newtons, that they can accelerate it quickly from some velocity, from rest to some velocity 4,000 meters per second. And the question is, how long really does it take for them to do that? Now, if I'm thinking with my with the kinematics equations, now I have the initial velocity, I have the final velocity. So that's 2 variables. I need a third variable to be able to get the other variables. So to get the time, I would need something else. And knowing the force and the mass, I think the acceleration is the best way. So the way I'm going to approach this is 2 steps. First, with F equals ma, I have F and m, I'm going to get a. And then with the kinematic equation, I'm going to find t with the appropriate kinematic equation. So the acceleration is proportional to the net force, inversely proportional to the mass. That's 4.9 10 to the 5 newtons divided by 5 kilograms. It's 9.8 times 10 to the 4 meter per second squared. So now that I know the acceleration and I know the initial and final velocities, I can use the appropriate equation in which, because this is a constant acceleration, I have the final velocity is equal to the initial velocity plus the acceleration times time. The initial velocity is 0, so I know then that the time is going to be the velocity divided by the acceleration. So when you put those numbers in, it's 4,000 meters per second divided by 9.8 times 10 to the 4 meter per second squared gives me roughly 41 milliseconds. Okay, now to question number 12. I would pause, go read the question head, and then come back for the solution. Question number 12 is about a soccer ball that's being kicked, and I'm given the 2 accelerations, the x and the y accelerations, and the question is asking about the magnitude of the net force. Now there are 2 ways to go about this. You could use the x and y components of the acceleration to figure out the magnitude of the acceleration, multiply that by the mass, and you get the magnitude of the net force. Or you can, from the x and y components of the acceleration, you can calculate the x and y components of the net force, and then you can square that with Pythagorean theorem to get the magnitude of the net force. I think I used the second approach, but it really doesn't matter which approach you use. So for me, I calculated the net force in the x direction, which is mass times the x component of the acceleration, and that comes out to roughly 350 newtons. And in the y direction, the mass times the y component of the acceleration comes out to roughly 473 newtons. And if you square that using the Pythagorean theorem, you find that the magnitude of the net force is equal to 587 newtons. Of course, you could have found it the other way, just like I've said before. For question number 16, again, pause, go read the question head, and come back. Question number 16 is the one where there is a man and a woman that are standing on ice. The woman pushes the man with 45 newtons towards the east, and the question is, what are the accelerations for both the man and the woman? Of course, when the man pushes on the woman with 45 newtons to the east, the reaction force from Newton's third law is that the woman will have a force on her that is 45 newtons to the west. Knowing both net forces and both masses, I can get both accelerations, which is basically proportional to the net force, inversely proportional to the mass. So for the man, it's 45 newtons to the east divided by 82 kilograms, and for the woman it's 45 newtons to the west divided by 48 kilograms. Now for question 28, again, like I said, you can read the question here and come back, and that's the question that is talking about the sun and the moon and the earth and their effect on the moon. And these are the things that are given. We're given the masses of the three objects. We're given their configuration in this sort of 90-degree situation. They're perpendicular. The line connecting the sun and the moon is perpendicular to the line connecting the moon and the earth. We're given the masses, we're given the distances, and we're asked what is the net force acting on the moon. I could calculate the net force acting on the moon from the sun and the force acting on the moon from the earth, and then I can sum that vectorially to figure out what the net force is. And of course these forces are gravitational forces, so I'm going to use Newton's universal law of gravitation. And what I'm going to do first is I'm going to calculate what happens to the moon due to the sun. And there the gravitational force is, of course, g, the mass of the moon, the mass of the sun, divided by the distance between them squared. So this is really an exercise of putting things properly in your calculator, and you figure out that the force is 4.34 times 10 to the 20 newtons. If you calculate the force, the attractive force between the earth and the moon, of course there is an effect on the earth. If the earth is pulling the moon is also pulling the earth. But we don't care in this problem about the earth and the sun, we just care about what happens to the moon. The attractive force between the earth and the moon is equal to g multiplied the mass of the moon, the mass of the earth, divided by the distance between them squared. And again, you put things properly in your calculator, you find that it's the same order of magnitude, which is 10 to the 20 newtons, but in this case it's roughly 2. So if I look at what is happening on the moon, I have the sun is affecting it, pulling it to the left, and the earth is pulling it down. And since this is a right angle triangle, the net force is basically, by Pythagorean theorem, it's equal to the square root of the horizontal component. I guess there's no horizontal or vertical really. It's x and y, I would say. So the x component squared plus the y component squared under the square root. And the trick here is to think of the 10 to the 20 as part of the unit, right? Because both forces are the same order of magnitude. I'm going to think of 10 to the 20 Newton as part of the unit, and I don't have to put that under the square root because it's common in both forces. So it's common in both components. So I'm basically finding out what this is multiplied by the unit that is 10 to the 20 newtons. And if you do this calculation, you find that it's 4.77 times 10 to the 20 newton. Next question is question number 29. Again, go read the question head and come back. But the idea there is that I have three masses on a line, mass A, B, and C, and I'm given the masses, and I'm giving the distances between them. And the question is, what are the net forces on each of the masses? And the forces between them are going to be gravitational forces. And the way I like to do this problem is I like to isolate each two masses and then look at the force that they exert on each other, and then look at each mass individually and figure out what the net force is. So first let's start with A and B. So if I look at A and B, the forces between them, of course, is an attractive gravitational force, and it's going to be equal to G times the mass of A, mass of B divided by the distance between A and B squared. I have the gravitational constant, I have both masses, and I have the distance between them is half a meter. So if I sub that in, I get 50 micronewtons. I like to write the equation like this, put all really label all the variables so that when I'm subbing in, I know exactly which mass I am putting in and I don't get confused if I get distracted for a second, I know exactly where I am and I don't lose my train of thought. It's also important if you find that something is fishy and you're going back to check, it's good to know what the equation was that you were subbing in, just in case you made some mistake. It also keeps things tidy, and it costs you literally 5 seconds to write the equation before you sub in. So after I'm looking at A and B, now I'm going to look at A and C, and the attractive force between them is FAC, and again it's equal to G MAMC divided by the distance between them squared, and distance between them now is going to be 0.5 plus 0.25, that's 0.75. So you sub in the numbers and you find that it's 6.6 micronewtons. And the last forces are between now B and C. And again, it's nice to draw the diagrams so that it literally takes you 5 seconds to draw the diagram, yet it saves a lot of trouble when you're trying to figure out what these forces are and what their directions are. So if I'm looking at the attraction between B and C, now this is going to be G multiplied by the massive B, the massive C, divided by the distance between them squared. And again, you sub in, you find that it's 85 micronewtons. And all of the forces, the direction of them are attractive forces. So now if I isolate A on its own, see how easy it is just knowing from these drawings, knowing what the force on A is. It's the sum, vectorial sum of these two forces. They happen to be in the same direction, FAB and FAC. So the net force on A is going to be the sum of these two forces, and it's going to be pointing in the positive x hat. I add 50 micronewtons to 6.6 micronewtons, I get 56.6 micronewtons in the x hat. If I'm isolating just B on its own, I find that it has a force to the left of FAB, a force to the right of FBC, and these two forces are, one of them is going to win over the other depending on which one is bigger. So that's why it's important to decide on a direction that is positive for x hat, and I'm decided that the direction to the right is positive, so that means it's going to be minus FAB, so minus the 15 micronewtons, plus the FBC, which is the 85 micronewtons, which is bigger, so you get 35 micronewtons to the right. And for C, you find that they're both pointing to the left, both contributions from the pull of A and the pull of B. So you add these both with the appropriate signs, and you find this is the net force on C. The next question is question number 41, and this question is just really to look at what it means to be a normal force. So this question is about the ratio between the normal force and the weight of a car that is on some incline, and the weight is always down towards the center of the earth, and the normal force is always normal to the surface, that is perpendicular to the surface. So if I'm looking at the normal force here, if I draw the free body diagram, the weight is going to be down, the normal force is going to be in the direction perpendicular to the incline. So that means if I look at the components of the weight in the direction parallel to the incline and in the direction perpendicular to the incline, I find that the one in the direction perpendicular to the incline is going to be W multiplied by cosine the angle. So if I look at the equation of motion in the direction perpendicular to the incline, I find that the normal force then is going to balance out with the component of the weight in the direction perpendicular to the incline. So if I look at the normal component of the weight, it's going to be W cosine theta, and then the normal force is going to balance with the normal component of the weight, which is W cosine theta. So if I look at the ratio between the normal, between Fn and the W, I find that it's equal to cosine theta. So whatever theta is, I get that ratio. The next question is a question number 54, and it's a simple one about a beam that is being pulled up by some force, by some tension in two cables that are making 70 degrees with the horizontal, and the weight of that beam is 8 kilonewtons, and the problem tells me that it's going up with constant velocity. So constant velocity just means that it's in equilibrium since it has no acceleration. So constant velocity or at rest means that it's in equilibrium. So being in equilibrium in y means that the net force is equal to 0. So the net force is equal to 0 means all the forces pointing up are going to be equal to all the forces pointing down. The forces pointing down is W. The forces pointing up are the two components of the two tensions that are in the y direction. So in the y direction, the component here is going to be t sine 70 degrees. Component on the other side is going to be t sine 70 degrees. So they're both going to be 2t sine 70 degrees. And from that, I can find the tension, which is what is called for. And that's 8 kilonewtons divided by 2 because there are two of them, and sine 70 degrees because that's the component in the y direction. I get 4.26 kilonewtons.